Researchers from the Zurich Institute of Technology have challenged everything we thought we knew about quantum mechanics. According to them, they've managed to put a visible object into a state of quantum superposition. This claim is mind-boggling because it means the quantum scale, which we believe to be far removed from our everyday reality, could suddenly be within reach. What mass or size would reveal the strange properties of quantum mechanics? Scientists from Zurich set out to answer this question and claim to have placed a crystal weighing approximately 16 micrograms, about the size of a grain of sand, into quantum superposition. Wait a minute. Wasn't it said that the quantum world is entirely beyond our perception, invisible to the naked eye, and impossible to grasp intuitively? So, what's happening now? How can a visible object exhibit quantum strangeness? In this superposition state, the crystal moves both up and down simultaneously, existing in two different states at the same time. This is essentially like Schrodinger's cat coming to life on a macroscopic scale. It seems we're now one step closer to experiencing the quantum world, not just theoretically, but through real-world observations. Just imagine, we're peering into the quantum realm with an object the size of a grain of sand. At this rate, science might soon reveal quantum oddities, not just in the lab, but even in our daily lives. It's not possible to determine whether an entity is governed by quantum mechanics solely based on its size or mass. In other words, we can't say, anything under 15 micrograms follows quantum mechanics, while anything above adheres to classical physics. Instead, we determine whether something belongs to the quantum realm by observing whether it exhibits quantum properties. If the scientist's claim is accurate and a grain of sand-sized crystal has been placed in a state of superposition, then we can indeed say that this crystal is subject to quantum mechanics. The fact that we can see this crystal with our naked eyes doesn't change the reality that it exists in two different states simultaneously. In other words, this crystal is no longer an object that strictly follows classical physics. It has become a quantum entity, displaying the strange rules of the quantum world. This demonstrates that quantum mechanics isn't confined to subatomic particles. It extends into the macroscopic domain as well. It seems the boundary between quantum mechanics and classical physics is far more flexible than we previously thought. Superposition, often illustrated by Schrodinger's cat, refers to a particle or system existing in a combination of multiple states at the same time. This is a phenomenon unique to the quantum world, something we don't encounter in the realm of classical physics. In all experiments conducted so far, this phenomenon was known to be possible only for particle-level entities. Moreover, this wasn't just a theory for us, it was a reality confirmed by experiments. But science is always full of surprises. It seems that wherever we look, we continue to rediscover the boundaries of quantum mechanics. Subatomic particles like electrons and photons can easily exist in a state of superposition. However, observing superposition at macroscopic scales is extremely challenging because environmental factors, such as thermal noise, quickly disrupt this delicate state. First, let's try to understand the concept behind the phrase existing in a combination of multiple states, which is fundamental to the definition of superposition. An electron isn't defined as being fixed in a specific orbit around an atom. Instead, it is described as being able to occupy multiple orbits simultaneously. This situation is represented in quantum mechanics by a mathematical expression called a wave function. The electron might be in one orbit, in another orbit, or even in a combination of both. During superposition, these orbits form a set of probabilities defined by the wave function. At macroscopic levels, superposition manifests differently. It is often observed through vibrational properties. For example, a resonator can oscillate downward or upward. However, in a state of superposition, the same resonator behaves as if it is oscillating both downward and upward simultaneously. This implies that a macroscopic object transcends the rules of classical physics and enters the domain of quantum mechanics. In conclusion, superposition can be observed in both the microscopic and macroscopic worlds, albeit in different ways. However, at macroscopic scales, stronger environmental effects make it highly challenging to maintain this state, requiring extremely delicate experimental setups. To better understand the study underlying this video, it is crucial to grasp one particular concept at this point. Each property can independently exist in superposition. For instance, the orbit of a particle in superposition can include all possible positions simultaneously. However, its spin might not be in superposition at the same time and could exhibit a definite spin value. This demonstrates that superposition doesn't have to encompass all properties of a system. Different properties can independently